test. So exam 2. Today?
Yeah, let's do it.
No. Exam 2 next Tuesday? No. Exam 2.
Is this going to be on the test?
So what would that be? That would be the 2nd, I think? March 2nd? Thursday, March 2?
For the next Tuesday.
Would you prefer that?
Yep, let's do that.
Okay. We'll keep it on a Tuesday.
So actually,
Oh, has spring break started by then?
next week is the last week. After next week, it's spring break.
Oh, okay. Then yes, let's definitely do it before spring break. Okay, so Thursday, 3-2. Okay, so that's it, hopefully. And topics, well, the topics are going to be everything up through centroids. And remember that these are cumulative, so you need to go back and refresh your memory on the old stuff. Yes. And so no structures. The next thing we're going to go into. Yes.
What about distributed loads?
Yep. All of the stuff in the centroids practice problems, assignment problems. So yeah, remember that it's cumulative. And anybody have any other questions about exam 2? Anybody have any homework questions? Yes. Okay. Do you have it with you? Not rigid body statics. That's the new one. So unless I wrote it down wrong. Usually, so the way I always intend to do it is like the first time through the problems, you do them all in order. The second time through, you do the evens. And then the third time through, you do the odds, so that you're doing everything twice over the course of the semester. So yeah, this is okay, so rigid bodies. Did we already do this in class, Naomi? Did we really? Okay. Naomi's job is to determine whether we've already gone through. Okay, well, I can, you know what, Naomi, is it okay if I just say a few general things about this problem? Okay. She's more strict about it than I am.
She didn't do this one thing 8 times. Are you kidding? I'm doing it. I'm doing it. Yeah. Way to tell your student what we're doing in class. Show her his boss.
Okay, so it looks like this. You have a beam at a 45-degree angle. And down at the bottom, there's a pin and slot joint. And up at the top, there's a pin joint. The length of the beam is 4 meters. And the mass of the beam is 850 kilograms. Holy moly. This angle is 45 degrees. And this angle is 20 degrees. And we want to calculate the reactions. So a free body diagram of the beam. We have the weight, so that's 850 times 9.81. And then if that's the direction of the slot, the force applied by the pin and slot joint is perpendicular to that. So I'll call that the scalar RA. And then up at the top, this is a pin joint. So we have an unknown force vector. Call that RB. How many equations are we going to get from this, from Newton's laws? Planar rigid body problems always give you 3 equations. So we know that we should get, well, in almost every case, we should get 3 variables. We know if we have more than 3 variables, we can't solve it. If we have less, then maybe one of the equations is degenerate or something. So I think I'm not going to go through the calculation, but this force here, the way to represent that is so if this is the coordinate system, we know that this, so say that this vector is parallel to the slot. So we know that this angle is 20 degrees. That's what we're given in the problem. We know it's 20 degrees from the vertical. And we know that this force is 90 degrees from the slot. That's RA. And so to figure out the angle of this, you go from the positive x-axis, 90, another 20, so now we're at positive 110, minus 90, and you're back at positive 20. And so that force is RA times cosine of 20, RA sine of 20. And then the 45-degree angle you're going to use for the row vectors. You know, like if you put your about point here, use that 45-degree angle to figure out the vector from the about point to where this force is applied and where this force is applied. Okay. Any questions about that one? What day did we do that, Naomi? She's like the, what's that called? The stenographer, court stenographer. Can you read that back? Okay. Okay, maybe February 9th, that does the whole problem. Any other homework questions you want to see? Yes. Okay. Oh yeah. This is a different one. Okay, so number 15. So there's a long axle that goes through these two pin joints. And there's some gears on it. I'm just going to draw them like circles. But there's one on the far end. And there's one right at the, nope, not at the midpoint, in between these two, the two pin joints. And the distances, it's 4 inches between these two. And then 3 inches between that gear and the next pin joint. And then 2 inches from the pin joint to the little gear. Okay, and then on the big gear, there are 2 forces applied. One this way that's 265 pounds, and then one straight down of 96 pounds. And then on the little gear, there's a force like this on the front. That's 192 pounds. And one going up to that same point of 530 pounds. And we have to figure out the reactions. Oh, the radii of the gears. The left gear has a radius of 1.5 inches. And the little gear has a radius of 0.5 inches. And we want to calculate the reactions. All right, well, the first thing to notice is there's nothing preventing this shaft from rotating. Okay? And so the only way that this would not rotate around its axle is if the moments applied by these forces on the two gears happen to equal each other. You know what I mean? There's nothing here fixed that prevents a rotation. It's free to rotate through this, and it's free to rotate through this. And so that means that we're not going to use a static equation for the, let me give a coordinate system. So let's use, it gives us one. The x-axis going this way, that's the positive x-axis. The positive y-axis going this way, and then the z-axis this way. Okay, so about what axis is this free to rotate? It's important to be able to see that. Yeah, right. It's free to rotate about the x-axis. So when this is a three-dimensional problem. So we're going to get 6 equations. But one of those equations is the one saying that the sum of all the moments about the x-axis is equal to 0. That's what you get if there's no rotation about the x-axis. Since this is free to rotate about x, we're not going to use that equation. Okay, so already before we start the problem, we're down to 5 equations. Okay, because I mean, you can calculate the moments produced by these two forces about the x-axis, and these will come out to give you something different than these will. And so this thing's rotating. So what we're going to do is, so it's rotating, but it's not moving this way along the x-axis. It's not translating in the y or z direction. It's not rotating like this. So that would be a rotation about the z-axis. And it's not rotating like this. That would be a rotation about the y-axis. Okay, so we have 5 equations. And then there's actually another equation that we're not going to use. Because if you look at the forces that are being applied, there's nothing producing any force along the x-axis. And so whether either of these two pin joints provide thrust or not, this thing isn't going to accelerate. So we're just going to skip that one too. So we're down to 4 good equations. We're not going to use the moment equation about x. And we're not going to use the force equation, Newton's second law. In the x direction. Okay, so let's draw a free body diagram. And what do we have? We have the applied forces here, that's 96 and 265. The applied forces on the other one, this is 192. And 530. Then we have the loads and pins. At the pin on the left, what kind of loads do we have here? So first of all, what are the loads that a pin joint can apply? We know that that point's not going to translate about the z-axis or the y-axis. So we know that there's a y component of a force and a z component of a force. There's also an x component of a force if there's thrust in the joint. So is there thrust provided by this joint? Yeah, I mean, it doesn't say anything about it. We're ignoring that equation anyways, though. That thrust would show up in the x equation of Newton's second law, and we're not using that. So we'll just treat it as a y and a z component. And then what about the couples? A pin joint can provide 2 couples too, right? One that prevents rotation about the y-axis, and one about the z-axis. In this case, are we going to include those couples? This is an important point. Whenever you have, we're not, and it's a very specific reason for this answer. Like the general answer is we only put those couples in if it's needed for equilibrium. The more specific way of thinking about it, and the way that it comes up almost all the time, is if you have two of these pin joints that are along the same axis, then you're not going to include those couples. If you don't, if you only have a single pin joint, then you are going to include those couples. So in this case, we have two pin joints along the same axis. We're not going to include those. So this joint applies a z component and a y component. And then over here, same thing. We don't know if it applies thrust. We don't care because we're not using that equation. There's a y component and a z component of force. No couples because we have the two pin joints in line. So over here, we have, I'll call this R-A-Y. I'll call this R-A-Z. And then over here, same thing, I'll call this R-B-Y and R-B-Z. Any questions about the free body diagram? And then let's choose an about point. I think I'll just do it right here. So rho, force, moment. This force RA is acting at the about point, so rho is 0. The force vector is 0, RAY, RAZ. Cross product is 0, 0, 0, because that force is at the about point. Rho vector is 0. And now we'll go to the top of that gear. So from the about point, we have to go 4 inches along the positive x axis, and then 1.5 inches in the positive y direction. So the rho vector is 4, 1.50. The force, I guess I'm just going to include both of these in a single force vector. So we have a 265 in the positive x direction, a 96 in the negative y direction. Yes, that was a test. So nothing in the x direction, 96 in the negative y direction, and then, what was it, 265. And what do you get for a cross product? For x? Okay. 1060? Okay. Okay. So those are the forces at that first gear, the left gear. And then we get to the second pin. The rho vector is 4 inches in the positive x direction plus 3 inches in the positive x. 700. So 700. The force vector was 0, RBY, RBZ. And the cross product is 0. And then negative 7 RBZ. And then positive 7 RBY. And then the last one is the forces on the gear. The row vector, for if we think of that as a single force vector with a negative z component and a positive y component. To get to this point, we go 4 plus 3 plus 2 in the positive x direction, and then 0.5 in the positive z direction. So the row vector is 9, 0, 0.5. The force vector is 0, positive 530, negative 192. And then the cross product, can someone calculate that for me? Okay. Okay. 4770, like that. All right. Now, Newton's second law says, so I guess I'm going to add all these up and then just cancel out the equation that we know we're skipping. So 0, RAY, RAZ, plus 0, negative 96, positive 265. Plus 0, RBY, RBZ. Plus 0, 530, negative 192 is equal to zeros. And we're skipping this equation. That doesn't do us any good. And then the moment equation says 0 vector plus 397.5, 397.5, 1060, negative, and negative 384. Plus 0, negative 7 RBZ, positive 7 RBY, plus negative 265, 1728, 4770 is equal to zeros. And before we started this problem, we said the x equation we're not going to use. Now you can see, so what you see when you look at the problem is that there's nothing to keep it from spinning along about the x-axis, right? And then mathematically you see it at the bottom there aren't any couples that would keep this thing at rest that would be able to counteract the fact that these two moments that are applied about the x-axis don't add up to 0. So that thing's going to spin. There's nothing, you can't use that equation because it's not static. This is something. You know, that equation just isn't possible. Yes, so yeah, right. I think, I'm sure that's what happened to me the first time I did it, was actually I went through first, saw that we got a 0 equals 0 equation. That's obviously not useful. And then get to this one, and that's not even possible. At least the first one's useful, or at least the first one's possible. What? Well, yeah, so I think the thought process should be that you get to this, and you see that this one's 0 equals 0. And you see that this one, something went wrong. And so then you can sort of think back physically, like, does it make sense that I don't get two useful equations there? If you can't think of any physical reason, then that's sort of a concern. But in this case, you'd look at those, notice something went wrong, look back and say, oh, okay, well, that actually makes physical sense. So I'm just going to go with the 4 equations I have left. And then the last thing we need is we can only have 4 variables since we only have 4 equations. And that's what we have, RAY, RAZ, RBY, RBZ. So we have 4 equations and 4 variables. Any other questions about that one? Okay. Any other homework questions? What about questions about the test? Are there any of those problems you'd like to see me do? Yes? That's what I meant, but I mean, I'm happy to do anything. We're about to start a new topic, so this works fine. Okay, so centroids number 6. We haven't done this one yet? We haven't done this one in class yet? Okay. What?
Did you put solutions to the test online?
No. Yeah, I don't usually do that. I guess if you want to see how to do any of them, just let me know. I can do them in class or in office hours or something. So centroids number 6. Okay, so there's a pin joint here, and it's connected to a horizontal beam. And there's a roller. These are all 1/3 of the length of the beam. The total beam is 1 meter, so this is 1/3 of a meter, 1/3 of a meter. This is 1/3. And then we have a distributed load that goes from the midpoint of the beam to here. It has a maximum distributed load of 10,000 newtons per meter. So this distance is 1/2 meter. There's no mass. We're not assuming any mass of the beam, and we want to calculate those reactions. Okay, so first let's figure out what the total force is applied by this distributed load, where we're gonna put the equivalent point force. So that triangle has a base of 0.5, a height of 10,000. We know the centroid's going to be a third of the way from the wall towards the point, so over here. Where this distance is 0.5 over 3, so that's 1/6. The total area is 10,000 times 0.5 over 2, so 2,500. Any questions about that? Okay, so free body diagram of the beam. Yeah, for any of those distributed loads, you never need Y-bar because the forces are all vertical, and so you can move that force anywhere along its line of action. Okay, so we have a downward force from the distributed load of 2,500, and this distance is 1/6. And then we have the force from the roller, I'll call that RA, that's up. And then at the pin joint, we have an unknown force vector, I'll call that the vector RB. That's it. So with any rigid body problem, you could write out the row vector, the force vector, the moment vector. But I mentioned last time that in any of these problems where you just have a horizontal beam, calculating those row vectors is so easy because it's all horizontal, and all the row vectors are horizontal, and that means that only the vertical components of the forces produce moments. I think you'll be happy in the long run if you just get used to doing those horizontal ones in your head. But I won't take off points or anything. Like, feel free to write out that table of row vectors and stuff if you're more comfortable with it. I think on these exams you'll always have plenty of time to do it. All right, so Newton's second law says 0, negative 2,500 plus 0 RA plus RBX RBY zeros. And then the moment equation. So as an about point, I guess I'm going to choose this. So for that 2,500 Newton force, what's the moment arm from the length from the about point to where that force is applied? This is a third, and then this is another sixth. So that's, what's that, 3/6? Yeah, right. I'm just not that fast. So 0.5. The force is 2,500. And then would that downward 2,500 Newton force make this beam rotate clockwise or counterclockwise around that hinge? Yeah, you can make it rotate like that. So that's positive. And then next is this force RA. What's the distance from the about point to RA? A third. The force vector is RA. And then would that force make it rotate clockwise or counterclockwise around the about point? Clockwise, so negative, yep. And oh, one thing that I talked to a couple people who've been confused about this. When you're doing it this way, don't put the signs into the forces or the row vectors. Just treat everything as a positive number, and then at the end, when you think about what those two things together, how will those two things together make it rotate? That's the only time you need to think about a sign. So even though this 2500 is down, it's like in the negative y direction, put it in here as positive, put this positive, and then just think about the direction of that rotation. And that's the only place the sign comes in. And then the last one is RB. That's at the about point, so that doesn't produce any moment. So this equation says 1250 is equal to 0.3 repeating RA, so 3750. RA is 3750. And then plug that into the first two equations, and you get RB is equal to 0 for x, and then for y, negative 2500 plus, so that's negative 1250. Is that right? Okay. Any questions about that one? Any other homework problems? How about any questions about the test? Any of the test problems that anyone would like to see? Yeah, sure. All right, so this one, these two objects connected by a cable. And the connection points are A over here and B over here. The coordinates of point A are negative 4.70, 1.71. And the coordinates of B are 9.40, negative 3.42. And we want to calculate two things. First, if the cable tension is 100 newtons, what's the force vector the cable applies to A? And then the second one is the same thing basically, but what's the force vector the cable applies to B, this time if the cable tension is T instead of 100. So if the tension is T, what's the force the cable applies to B? All right, so for part A, we know the magnitude of that force, which means we know that force vector if we just come up with a unit vector in this direction. We know the force vector is in that direction. And so a vector in the direction that we want is B minus A. So that's 9.40, negative 3.42, minus negative 4.70, positive 1.71. And 14.1. And then subtract these two, and you get negative 5.13. That's in the direction of that force vector. It just isn't a unit vector, so now we have to divide by the length. Or if you have a TI-89 or Inspire, it'll just do that for you with the unit vector program. So the magnitude of that vector, the length of that vector, is 14.1 squared plus 5.13 squared square root. And then the unit vector is 1 over that length times the original vector, and you get 0.94, negative 0.342. And so then the force vector is 100 times that unit vector, so 94.0, negative 34.2. And then the second one, you could go through that whole process again. That wouldn't be a problem. You have plenty of time to do it. Or you could just recognize that now we're looking for a unit vector this direction, which is just the opposite of what we had before. You can just switch the signs on the unit vector. So the unit vector now is negative 0.940, positive 0.342. And so then the force vector, since this time the tension is T, the force vector is negative 0.940 T, positive 0.342 T. I forgot to mention this before, but if you feel like, a lot of times people will write something on one page and then they'll write their answer on a different page, and I won't see what's going on. And so I'll give you the score based on something, whatever. If something happens and you don't feel like I scored your test right, just try to bring it to me in the next week or so, and I'd be happy to, look at it again. Any other problems you'd like to see on the test? Okay. That's it. That's not it for class. That's it for review. Now we're going on to the next thing, the next big thing. structures. And structures is the main topic in this class. The most important topic in this class. And it has to do with collections of rigid bodies connected by joints. Okay, well, let me give an example. So, for example, you could have a bunch of rigid bodies connected by pin joints. All these dots are supposed to be pin joints. Let's say there's a roller down here, and then let's say there's a downward force here of F1, and there could be a distributed load here. With a maximum distributed load of Q. And we want to know what are the external loads on each of these members. The main reason that you'd want to do a calculation like that is it's the first step in figuring out if you're using a certain material and like certain geometry of these bodies. Are we nervous, concerned that any of these bodies are going to break, or are they going to deform more than we want them to? Or if you're doing it as a design problem, you could do these calculations and then say, okay, what kind of materials do these have to be made out of? Like what's the cheapest metal that we could use for each of these members? Or what's the smallest thickness that we need? I teach, so of all the things that I teach in this class, this topic is the one that I'm going to do the most differently from the way it appears in textbooks. I'll still tell you the way that they do it in textbooks, but we're not going to spend a lot of time on it. I think this is a better approach. So mainly, this is the idea. I teach a single Enroll approach for structures. Where textbooks, the ones I've seen, break structures up into two different categories. And these categories are trusses and frames. And so I just want to explain like what my thinking is on doing it this way. Why do I do that? So first of all, you don't have to, if you have one approach that works for every kind of structure, you don't have to categorize things. And sometimes the rules for categorization can be harder to remember than the approach itself, you know? And so like in 6 months when you're done with this class, I think there's a very high likelihood that you would go back and miscategorize some structure, get answers that aren't accurate because you're approaching the wrong thing. So it doesn't require categorizing structures. And remembering and applying multiple approaches. Second, and this might be an even bigger one, there are a lot of structures that don't fit into either of these two categories. So the approach that we're going to deal with works on everything. So it works on any structure. Even ones that aren't trusses or frames.
Shelves outline teach it more like the standard?
Yeah, it does. And like I said, I'll talk about, so the way that I'm doing it is pretty similar to the way that people usually teach frames. Some little differences. But people treat trusses very differently. And I'll talk a little bit about that truss simplification. We're just not going to do most of the problems that way. And then the third one is, I just think this is a better way, like this gets more to the fundamentals. It uses the fundamentals, so I think it helps you sort of, you know, I'm going to say it gives a like a sort of a deeper understanding of what's going on. Okay, and then what would they say? Why don't they do that? And I think the answer is, there's really just one answer. These, what? Yeah, exactly. The simplified approaches cut down the number of equations, sometimes by a lot. You know, reduce the number of equations needed. So they're easier to do by hand. My, answer to this is these approaches have been in textbooks since, I don't know, since engineering school started, basically. And there weren't hand calculators, and then when there were hand calculators, they weren't able to do vector calculations very easily and stuff. It wasn't easy to solve big systems of equations. Now that you can You can do vector calculations in your calculator. You can solve big systems of equations with the reduced row echelon form. The advantage isn't as big as it used to be for those simplified approaches. Not to mention that, when these approaches were developed, there were people whose job it was in engineering firms to sit and do truss calculations by hand. There weren't other ways to do it, And so having an approach that went really fast by hand, was an important thing. That's not true anymore. I mean, now, if you wanted to do these calculations for a company, you'd write software that did it. And so to me, it's more valuable to get sort of an overall understanding, come up with a systematic approach that you could create a program out of. So that's why we're going to focus on this. And it's going to make you better people. That's not as important. Yeah, I don't care as much about that. That's just like a side effect. Yeah, exactly. Right. I'm going to start with just an example problem. We'll just sort of reason our way through, and then after that, I'm going to give you a set of steps that you can follow that'll kind of systematize the way we did this. That's a word. Yes. I'll start by working through an example problem. I'm not sure if we're going to get all the way through this. And then once we get through this, I'll give you a careful set of steps that you can follow for every problem. So then I'll give a careful set of steps. All right, so here's the first example we're going to do. So this is an equilateral triangle connected by pin joints. The lengths are all 1 meter. And all the angles are 60 degrees. And let's say there's a force vector of 500 newtons here, and a force vector of 500 newtons here. Structures go like if you think of all possible collections of rigid bodies connected by joints. This is obviously a pretty simple one. But the way that I've set this up, this actually doesn't fall into the category of trusses or frames. So with the usual, textbook approaches, you couldn't solve this problem. The problem in this case is that we have a force applied at the pin joint there and one applied in the middle of the member there, and there's nothing you can do with those approaches. I'm going to first just label all this stuff so we know what's where. I'll call that body 1, that body 2. And then these pins, I'll call this one A, B, C. And I'm going to isolate each member. And come up with Newton's second law and the rotational equation for each. And in order to cut down the number of equations, one important thing that I'm going to do is I'm going to treat every pin, so every pin will be treated as part of the lowest numbered member it connects. All that's doing is just saying that anything that happens, like this 500 Newton force that's applied to this pin at B, we're going to say that that force is applied to member 1. Okay. So it's a bookkeeping thing.
So by number, do you mean the number you've assigned?
Yeah, that's right. So, and it's totally arbitrary. Like, I could have numbered these opposite, and then we would say the 500 Newton force was being applied to this member. All we're doing is making sure that things that are happening at the pin are only treated as happening once. Otherwise, if we said this 500 Newton force was applied to 1 and to 2, that would be the equivalent of a 1,000 Newton force there, and we get the wrong answers. Did you have a question? All right. Okay.
Yeah, it wouldn't.
Okay. So let's do member 1. So free body diagram of 1. There's a pin down at the ground, so that's an unknown force vector. I'll call that RA. And then up at the top, that pin is part of member 1. Member 2 is touching the pin, and the 500 Newton force is touching the pin. So here we have the force on member 1 by 2. And we also have the 500 Newton force. And I'll put the about point here. So row vector, force vector, moment vector. So I'll start at these two forces at the top. The row vector is 0. First I'll do F12. And the cross product 0. And then the 500 Newton force, the row vector 0 again. The force is 500, 0. Cross product is 0. And then RA, row vector, that has a length of 1. And this angle is 60 degrees. So you can think of this one as 240. So 1 times cosine and sine of 240 gives you negative 0.5, negative 0.866. The force vector is RAX, RAY. And the cross product says negative 0.5 RAY plus 0.866 RAX. So Newton's second law says F12x, F12y plus 500, 0 plus RAX, RAY is equal to zeros. And the moment equation says 0.866, I'm just rearranging these, but 0.866 RAX minus 0.5 RAY is equal to 0. Okay, so can we solve this yet? In a rigid body problem, we would be able to, but in this case, we have three equations. How many variables do we have? 1, 2, 3, 4. So we can't solve it yet. And so now what we have to do in a structures problem is we have to go on to the next body. These are three good equations that are going to be part of our system of equations that we're going to solve at the end. So free body diagram of body 2. So what's in contact with body 2? Well, it touches the pin at B. So there's a force on 2 by 1. And Newton's third law says I can write that as negative F12. What about that 500 Newton force? That's not there. That's applied to member 1. Then midway down the member, there's a different 500 Newton force. And then there's the connection between the pin joint and the ground. Call that RC. So row vector, force vector, moment vector. I'll put the about point here. So for RC, we have no row vector. Force vector is RCX, RCY, and the moment is 0. Then the 500, row vector is negative 0.25, positive 0.433. Force vector is 500, 0. And so the cross product is negative 216.5. And then up at joint D, row vector is negative 0.5, positive 0.866. Force vector is negative F12x, negative F12y. And the cross product is negative 0.5 F12y plus 0.866 F12x. Okay, I know I'm running over. I'll be done in 2 minutes or less. So Newton's second law says RCX, RCY plus 500, 0 plus negative F12x, negative F12y is equal to zeros. And the moment equation says negative 216.5 plus 0.866 F12x minus 0.5 F12y is equal to 0. Yep, thank you. So that's positive, and that's positive, yep. Now what we have is 3 equations here, 3 more equations here. We have 6 equations. And how many variables? In the first set of Newton's laws, we had F1, 2, that's 2 variables. RA, that's 2 more, so we had 4. Now we've only added 2 more, RC. And so we have a system of 6 equations, 6 variables. You can solve it easily by reduced row echelon form, and it'll give you all those forces. Any questions about that? Okay.